Exercise 227 introduces the third pattern of resonance, and that is when you have a lone pair adjacent to a positive charge. So it says for each of the compounds below, locate the lone pair adjacent to a positive charge and draw the resonance structure. Okay, so the first step is just to draw the lone pairs. Remember, carbon only has a lone pair if it has a negative charge. None of the carbons in this molecule has a negative charge. The other atoms, nitrogen and oxygen, the ones that are different from carbon, and the term for those are heteroatoms. Hetero just is a Greek prefix meaning different. The heteroatoms, like nitrogen here, need a total of 8 electrons drawn around them. Now this nitrogen has 3 bonds, and remember in each bond there are 2 electrons, so this nitrogen has 2, 4, 6 electrons around it already. But it needs 8, so you would add 2 more in as a lone pair. Okay, now that we have that lone pair drawn in, it's easier to see that we have this third resonance pattern, a lone pair adjacent to a positive charge. We have a lone pair. If you go 1 atom over, you're at an atom that has a positive charge. So, first step, so we know we have resonance, so we draw that. The brackets that tell us, that warn the world that none of the structures we're about to draw are the true structure. The true structure is the average of them all. And we'll just copy the molecule. Remember, when carbon has a positive charge, that means it only has 3 bonds. So here you just have 1 invisible hydrogen. And so the other thing you'd want to know, in addition to recognizing this pattern, is how the electrons move. What is the pattern for the curved arrows there? And for this pattern, the curved arrows go to form a new pi bond toward the positive charge. That should make sense. Negative electrons attracted to a positive charge. So you draw that special resonance arrow that tells you to average the structures. You can copy the molecule you have. Everything's going to stay the same. And now we can just move the electrons. So anywhere where you have the tail of a curved arrow, that's a place where electrons are going to be moving away from, so you erase those. Anywhere where you have the head of a curved arrow, that's a place where electrons are going to be arriving, so you draw them in. If the head of a curved arrow points at a bond, like it does here, then the electrons arrive as a bond. So we've got that. Then you would just want to think about the formal charges. For this carbon on the left, carbon is in group 4a, so 4 minus 0 dots, and here we have 1, 2, 3, 4 lines. So 4 lines, that's 4 minus 4. That carbon has a 0 charge. And then the nitrogen. Nitrogen is in group 5a, minus, there are 0 dots around the nitrogen now, and 1, 2, 3, 4 lines. So that nitrogen has 5 minus 4, or a positive 1 charge. So that's it. There's your resonance structure. The true structure would not ever look like this, and the true structure would not ever look like this. The true structure would always only look something like this. There's an in-between bond there. It's stronger than single but weaker than double, and partial charges on these 2 atoms. All right, and remember, the meaning behind this resonance is that it makes the molecule more stable and more rigid. The more resonance it has, the more stable and the more rigid. So we can see that same pattern here. Remember, the third pattern is a lone pair right next to, adjacent to, a positive charge. So here, in order to see that, we would want to draw all the lone pairs in. And in this molecule, the lone pairs will only be on the heteroatom. A carbon only gets a lone pair if it has a negative charge, and none of the carbons in this molecule has a negative charge. So we'll just look at the atom that's different from carbon, the nitrogen here, the heteroatom, and we'll make sure it has 8 electrons around it. There are 2 electrons in each bond, and the nitrogen has 2 bonds, so it has 4 electrons already. That means it needs 6, 8, or 2 lone pairs for a total of 8 electrons around it. The curved arrow pattern here is that the lone pairs go toward go to make a bond toward the positive charge. All right, so we know we have resonance because we have these lone pairs right next to a positive charge. And so we'll draw the resonance structures, first drawing those brackets that warn everybody that none of these structures is going to be true, only the average of them is the true structure. And I'm just going to copy the molecule exactly as it is. Okay. And so you get the curved arrow bringing that lone pair down to the bond. You draw the special resonance arrow that tells you to take an average of all the structures. Copy the molecule. Wherever you have the tail of the curved arrow, electrons are moving away from there, so erase those. And wherever you have the head of a curved arrow, that's where electrons are arriving, so you want to draw them in. If the head of a curved arrow points at a bond, then you draw in the electrons as a bond. You can see now that this carbon here has 4 bonds around it, so it must have a 0 charge. And the nitrogen, if we calculate the formal charge on that, it would be 5 minus, because it's in group 5a, 2 dots and 3 lines, 1, 2, 3. So 5 minus 5, it now has a 0 charge. And there it is. That's your resonance structure. So the true molecule never looks like this, never looks like this. It always only looks something like that. With partial positive and negative charges and a partial bond there, an in-between bond, a bond stronger than single but weaker than double. And the fact that you have resonance means this bond is more stable and more rigid. Okay, last but not least for this one, you'll look at this and we're checking for our third resonance pattern. Really, you would go through all of them and say, do you have an allylic lone pair? Well, first let me draw in all the lone pairs. None of the carbons here have a lone pair because carbon only has a lone pair when it has a negative charge, and none of those carbons have a negative charge. So we just have to worry about the atoms different from carbon, the heteroatoms, like oxygen. These need 8 electrons around them. The oxygen already has 4 electrons around it. So we just need to draw 6 and 8. So 2 lone pairs gives it a total of 8. Now that we have the lone pairs drawn in, we can go through each pattern. We have lone pairs, but they are not allylic. We don't have any double bonds in this, so these lone pairs can't be one atom away from an atom in a double bond. So no allylic lone pairs. We have a positive charge, but the positive charge is not allylic, because to be allylic, you have to be one atom away from a double bond, and there's no double bond in this molecule. But the lone pairs are adjacent to a positive charge. If you go one atom over, you're at an atom that has a positive charge. So this does have resonance. So we draw those brackets that warn everybody, watch out. The molecules we're drawing are not real molecules. The average of them is the real molecule. And notice the curved arrow pattern for this third one is that the lone pairs go to form a bond toward the positive charge. So these lone pairs will go to form a bond toward the positive charge. That'll give us our resonance structure, so we draw that special resonance arrow with the one line and two heads that tell people take the average. And you copy that molecule that you have drawn. Now, anywhere where you have the tail of a curved arrow, that's a place where electrons are going to be moving away from, so you erase those. Anywhere where you have the head of a curved arrow, that's a place where electrons are arriving, so you want to draw them in. If the head of a curved arrow points at a bond, then you draw those in as a bond. The electrons arrive there as a bond. All right, formal charges. Well, notice this carbon here has 4 bonds around it. So 4 minus 4, 0 formal charge. And the oxygen is in group 6A, minus 2 dots and 3 lines. That's 6 minus 5, positive 1. That oxygen has a positive 1 formal charge. And so that is your resonance structure. So the true structure never looks like this on the left, never looks like this on the right. The true structure always only looks like that. So this bond is an in-between bond, stronger than single, weaker than double, and there's a partial positive charge on each of the 2 atoms between them. And the fact that this has resonance, the fact that this molecule has resonance means that it's more stable and more rigid. And that is the third resonance pattern, a lone pair adjacent to a positive charge.